Okay, welcome to another video. This video will look at an example of linear programming with uncertainty. We'll kind of look at the same example, but approach it from a robust optimization perspective using chance constraints. We'll look at a little bit of simulation, and we'll also look at stochastic programming with Recourse. So the problem that we'll look at was one of the homework problems from week 1. Here we've got a computer center scheduling problem. I've modified the problem slightly. And so whereas originally we sort of had a minimum number of employees during each of the shifts, I've now changed it to the computer center is receiving help tickets. And here are the average number of help tickets that they're receiving each hour. And a typical worker or consultant can clear about 10 tickets per hour as their sort of service rate or their rate of responding and answering to those tickets. Okay, and so we'd like to meet the average demand here. And so if we actually take the 10, if we take the number of tickets divided by the 10 tickets per hour per person, we'll get back to what was the minimum number of staff on duty during each shift. Okay. But in a little bit, we're going to play around with both the tickets coming into the help center as well as the rate at which consultants can service those help tickets. And we'll add some uncertainty to both those on either side. And so it won't be as simple as just dividing these numbers by the 10 tickets per hour. Okay. So still have two types of consultants that can be hired full-time and part-time. Full-time workers work 2 consecutive shifts for a full 8 hours of work. Part-time workers only work for one shift, 1 4-hour shift a day. There's a slight difference in pay there. And we're required that there are at least 2 full-time consultants on duty for every part-time consultant. They don't want to staff the center solely with part-time consultants. Otherwise, they probably would because they're going to pay them less. They want at least a certain number of full-time there, probably because they have more experience and can maybe deal with what might be more complicated help tickets. Okay. And he wants to essentially determine the full-time and part-time workers that minimizes the daily staffing costs. So we introduce variables for full-time and part-time for each of the shifts. Note that the full-time workers work in full-time 1, work during shifts 1 and 2. Full-time 2 works in shifts 2 and 3, and full-time 3 works in shifts 3 and 4. And so looking at their total pay per day, it's $320 for a full-time worker and $120 for a part-time worker. Here's the total number of full-time workers when we add them up, and here's the number of part-time workers when we add them up. So that's our objective function. Here are our constraints. We want 10 times the number of workers working, either full-time or part-time during that first shift, to be more than the 40 help tickets that we expect to come in. And that's how it works for the rest of the constraints. Note for this problem, we could divide the 10s over to the other side to get just the number of workers. But I'll leave it on this side to kind of keep it as is so that we can kind of play around with those sources of uncertainty in just a bit. And then these 4 constraints are looking at the ratio of the number of workers full-time to part-time during each shift. And so on the left are the number of full-time workers working during the shift. On the right is 2 times the number of part-time workers, and we need the full-time workers to be at least twice the number of part-time workers. So here's the same solution that was kind of presented to the homework problem. I've made just one slight change. I've made a vector here for the help tickets of 40, 80, 160. And then for service rate, I've just made a vector of 10 4 times over. And so I'm repeating the value 10 4 times. Okay. And so here you'll notice I've added that service rate into each of those constraints as well as the help tickets. And so for the first shift, that's the service rate for the first shift, help tickets for the first shift, and so forth for each of the 4 shifts. And then here's our kind of ratio constraints. We solve it out and we should get the exact same solution that you got for the homework, which is 3 full-time workers starting first shift, 3 full-time workers starting second shift, 4 full-time workers starting third shift, and then 1, 2, 3, and 2 part-time workers during each of the shifts. So that ends up with a total of 10 full-time workers and 8 part-time workers and a total daily cost of $4,160. Okay. So nothing unusual about that. That's a kind of straight up linear programming solution. I will say that we set both of our variable types for the full-time and part-time workers to be integer variables because we can't have half a worker. And so we're only looking at a whole number of workers. And so underneath the hood, this is actually an integer linear program, not just a linear program. We'll talk about those more next week. But it kind of solves out exactly as we've been seeing before. Okay. Critique here is that the solution we generated only meets the average workloads with the average ticket clearance. We might expect that occasionally we get more tickets than average and or where the workers are less productive than the average. And so especially troublesome is the combination of both when we get more tickets and they're less productive. Could be for many reasons. Maybe the tickets are just more complicated as well. Not necessarily that people are slacking off when there's a lot of work to do. But this can cause some of the help tickets to be delayed, and kind of there might be sort of a ballooning of the time for these help tickets to get answered. Okay. Next term for kind of the advanced OR class, we'll actually look at queuing theory, which will kind of be able to dive into the analysis of kind of how we expect the system to behave over time if kind of tickets are arriving at a certain rate and tickets are getting answered or serviced at a certain rate, and then there's sort of a queue or a backlog of tickets. I love queuing theory. We'll talk about that next term. But for now, we're going to make a simplified version for this one. Okay. So let's look at it first with robust optimization as our lens to view this problem. And let's say Larry's boss wants every help ticket to be answered within 1 hour. Okay, that's maybe a little bit hard to analyze. And so we'll simplify that condition slightly by changing it to be that we want the number of tickets that could be processed in an hour. So essentially the processing capability of for an hour to exceed the number of tickets that arrive in an hour. Okay, and so ticket processing capacity would be the service rate, which is the number of tickets per hour per person multiplied by the number of people working during that hour. And we want that to exceed the number of tickets that come in. We might expect that even if there's maybe slightly more in an hour, more tickets that come in than get serviced in an hour, that like there maybe just be a little bit of a backlog, and possibly that could get smoothed out during the next hour. And so this isn't quite exactly what Larry's boss is asking for, but it's maybe the easiest way that we can analyze the problem. You could maybe kind of break this down into smaller chunks of time if you wanted to, but we'll look at it at it on the hour. So Larry looks back at the past 3 months of data from the Solution Center, and he comes up with a range of between 8.5 and 11.5 tickets cleared per person per hour when they're actively working or when there's a backlog of work. You'd probably actually estimate this number by looking at the time taken to answer a ticket and then doing the reciprocal of that to get the number of tickets per time. And then he also found the following ranges for the number of tickets that come into the computing center. And sort of for each of the different shifts, we sort of expect a different range of number of tickets. So for that first shift in the day, fewer tickets, anywhere between 25 and 57, and so forth for each of the other shifts. Okay. The big idea behind robust optimization is that we analyze the worst case scenario. So in this problem, the worst case would be having the lowest possible service rate and the highest number of tickets coming in an hour. Okay. And so the lowest service rate is 8.5, and that's what we'll use as our service rate in our constraints now. And we want to use the max number of 57, 104, 127, and 81 as the number of tickets coming in for an hour. And so we use the combination of sort of the lowest rate of tickets being serviced and the highest number of tickets coming in that hour to get sort of what's the worst case as far as what would we need to staff to cover it in that worst case scenario. So all I've done here is I've changed the number of help tickets in an hour from their average number to their max number, and I've changed the service rate from 10 for all 4 hours, all 4 shifts, to be 8.5 for all 4 shifts. So sort of moving that to its lowest value. Otherwise, the rest of the code for the problem is the same, and it will solve out the same. But this time we'll get a solution where the staffing cost or the objective value is 6,680. The new solution has us having, let's see, that's 16 full-time workers and 13 part-time workers. So we've increased the number of both full-time and part-time workers to handle this worst-case scenario. And if we kind of look at the ratio of the objective values to the original scenario relative to this robust scenario, we're going to be paying about 60% more in staffing costs in order to meet this worst case scenario. So, yeah, if it's absolutely a hard constraint and you must answer every ticket within the hour that it arrives, or maybe the way we analyze it, you must be able to process more tickets in an hour than actually come in, then that's what you got to do. You got to pay 60% more in staffing costs in order to handle that worst case scenario. Now, the downside is when it's not the worst case scenario, you're going to have a lot of people sitting around. And so unless you have something productive for your consultants to do when it's not the worst case scenario, this seems very, very inefficient. Okay. And so robust optimization, good strategy when your constraints are hard constraints. They absolutely must be satisfied. There's no recourse if you violate them. Okay. On the other hand, we probably actually do have some recourse. If there's an hour where more tickets come in, we could just like let them get answered the next hour and kind of have a little bit of a backlog. As long as the backlog isn't too high, Larry's boss might not actually be as angry. Or maybe Larry has some ability to kind of pull some strings and bring in extra work to deal with any backlog that might kind of pile up. Okay. And so Larry negotiates with his boss and decides that it's okay if some hours have more help tickets arrive than served. But Larry's boss is okay as long as it's less than 5% of the time. Okay. So looking back at 3 months of data, instead of just taking the best and worst case scenarios, or really the worst case scenarios, Larry does a little bit of modeling. So he looks at the service rate of his teams, and it looks to be normally distributed with a mean of 10 and a standard deviation of 0.5. So kind of looks at it, that seems pretty reasonable. Modeling it with a mean of 10 and a standard deviation of 0.5. Larry also models the number of help tickets per hour with a Poisson distribution with means that match the average values from the original problem. Okay, so Poisson distribution is a great way to model a certain number of events happening in a fixed period of time. And so if we look at 1 hour windows and those events being help tickets arriving, Poisson distribution is a great way to model that. In practice, you might actually use an over dispersed Poisson, but for our problem here, that's pretty good. The big idea behind it is that you want to come up with some probability distribution for those parameters that you have uncertainty for. Okay, and in this scenario, looking back at historical data is a good way to come up with those distributions. To be honest, what you could do is you could also just sample from historical data as far as, okay, I've got 100 past days, and I know that during the 100 past days, here's how many people came in each hour in the first shift, and then just sample from that to get a distribution. That also work. So here's sort of our models for the two unknown or uncertain parameters of the problem. And so what we want to do is we want to kind of find out their 95% point in the direction that is also going towards the worst case scenario. So we want to look at a lower bound for the service rate and an upper bound on the number of tickets. Okay. But unlike the robust optimization, we don't have to go all the way to the extreme. Okay. We just want to go sort of 95% of the way there. So for a normal distribution, we want the lower bound. And so we're going to look at the 5th percentile. So Q norm, Q, and then the name of a distribution in R will give you essentially the percentile function of you give it a percentile in, and it will give you the value out at that percentile. And so for a mean of 10 and a standard deviation of 5, the 5th percentile or kind of 5% along the data is a value of about 9.2. So 9.2 is larger than 5% of the possible service rates and less than 95% of the possible service rates is maybe one way to think of it. Similarly, we can do the same thing for the Poisson distribution. Here we're looking for the upper bound, and so we'll look at the 95th percentile, and we can do it for each of the different averages. So here are the sort of averages, average tickets per hour. We put those into the Poisson, Q Poisson, and that will kind of give us a percentile. And we'll get values of 51, 95, 117, and 73. And so here are sort of reasonable upper bounds that we should stay less than 95% of the time. It's maybe interesting to compare these numbers, 51, 95, 117, and 73, to the numbers that we got for those hard upper bounds when we did the robust optimization. And you'll notice that the ones for the 95th percentile are not quite as extreme as the ones that we use for robust optimization. To be honest, for robust optimization, I think I did the 99th percentile to get these numbers using the same Poisson distribution. So that was sort of maybe a little bit more extreme than what we're ending up with here. Okay. So code is the same as the original, is the same as the robust. The only thing that we're changing here is what we're using for the number of help tickets, and then what we're using for the service rate. It's the same service rate repeated 4 times. It's just taking the value of this 9.177, okay, and putting that in there 4 times. And if you go ahead and solve that out, the objective value is 5,680. We're going to be scheduling more people per shift, but now we're only spending about 36% more or 37% more than the original, which is a lot better than 60% more. And so we're being conservative. We're protecting against what might be a low probability event, right? We're kind of 95% sure that we won't go over these constraints. And it's costing us 37% more than our base level. That seems pretty reasonable. Definitely less extreme than sort of pushing it all the way to the extremes that robust optimization required us to do for what might be much more rare occurrences of hitting those extreme upper bounds. Okay. Yeah, and we can do this as long as those constraints are soft. As long as Larry's boss is okay that there's going to be the rare hour where the computer center gets more help tickets than they can actually deal with. Okay. Let's look at the solution that we get from the chance constraints formulation. Let's do a simulation to see how often we'd actually violate those chance constraints. Okay. If there was only one source of uncertainty, then we'd say, oh, it's going to be exactly 95% of the time, or approximately if we're doing a simulation. But in this scenario, we've got two sources of uncertainty, both the service rate and the number of tickets. And if we think about it as well, we're actually looking at this every hour. And so there's 16 hours in the workday for this center. And so really we're sort of repeating these chance constraints 16 times. And so in a given day, there's sort of some compounding of the chance that there's at least 1 hour that goes outside of the constraints. Okay. So, yeah, here's the total number of workers at each of those hours. We'll do a little bit of simulation where we take the number of workers, which is now we're fixing at those values. We're no longer optimizing here. We're just saying these are the number of workers we have. Let's simulate the service rate and the number of tickets and see if we had more tickets cleared than tickets arrived. Okay. So I'm going to jump over to the R code to show you what the R code for this looks like. So here's the same R code here. For reproducibility, we'll use set seed so that it gets me the same answers every time I run it. In practice, you just kind of run it and let the random number generator take over. So I've set it up so that there are 16 hours in the day. There are, or 16 hours in the workday. Here are the number of workers, and we're kind of repeating those 4 times each because there's 4 hours in each shift. And then, yeah, I've added some names there. And for the mean tickets, those are the same mean tickets. Again, we're sort of repeating them 4 times because there's 4 hours in each shift. I'm going to do 10,000 simulations here. And let's go ahead and run this chunk. I'll show you what we get for the right-hand side. So the right-hand side is the number of help tickets coming in. We're generating those with this rPoisson function, rPois. Anytime you see R in front of a distribution name it's going to generate random numbers from that distribution. And so we're going to generate one number for each simulation and for each hour in each simulation. We're going to use lambda, which is the parameter of the Poisson distribution, equal to the mean tickets. This kind of reforms it into a matrix with simulations going down the rows and the hours of a day going across the columns. And yeah, so now let's look at that and look at a summary there. And so here's the distribution of all the tickets that arrived at from 8 to 9. And we see that the mean value is right around 40. Same for from 9 to 10, 10 to 11, 11 to noon. But if we look at the tickets that arrived from noon to 1, there we see that the average goes up to 40. Okay. We're not kind of thinking of this as being any sort of continuous distribution throughout the day, but rather for each of the 4 hours in the shift, same mean, next 4 hours, same mean, and so forth. You could definitely go much more involved and break this up to down to the hour or the half hour and kind of have different rates throughout the shift. But there's enough kind of moving parts here that we don't need to go down to that level. And so here's it for all the other shifts of the day. Maybe interesting, like you might pick out, okay, what's the max value in each shift? So the max number of possible tickets in that hour. And yeah, these are generated by the Poisson distribution. So if we look at the left-hand side, the left-hand side looks at a normal distribution with number of sims times number of hours. mean 10, standard deviation 10. And then I'm doing a matrix multiplication to multiply it by the number of workers during that shift. Don't worry too much about kind of how I sort of jerry-rig this together to work, but essentially I'll take the randomly generated service rate, multiply it by the number of workers in that hour to get the number of tickets cleared in that hour. So if I look at solution left-hand side, here I'll see that, well, on average, I'm clearing 60 tickets in the first one because there's 6 workers and they're each on average clearing 10 tickets per hour. Same for the first 4 hours. And so kind of my average kind of capabilities is 60, whereas the average number of tickets coming in is only 40. So we've got some excess capacity there on average, but you'll notice that we've sort of lined it up so that we're more likely to be covering the extreme case of what was kind of the max number of tickets for the right-hand side. Okay. So once we've done that, so that essentially runs the ticket, runs the simulation. Now we've got simulated values for the left-hand side, simulated values for the right-hand side. Let's compare them against each other. And so if we take the left-hand side greater than or equal to the right-hand side, that would give us a whole big matrix of trues and falses. Trues being when the left-hand side is actually bigger than the right-hand side, and falses when the left-hand side is not bigger than the right-hand side. And so it looks like if we look at individual hours, there's a 99.4% chance that an individual hour will satisfy its constraint. That's actually pretty good. That's much better than our 95% that we thought we'd get. And that's mostly because we have 2 sources of randomness going on in each of those constraints, the service rate and the number of tickets. And it's sort of unlikely that they both are going against us at the same time. And so in that sense, we actually do better because there's 2 sources of randomness in the same constraint. Okay. However, if we look at the day level, there's 16 hours in the day. And so the chances compound over the day that we'll have at least one bad hour. And so if we look at each of the rows, and so here I'm using the apply function. 1 here means apply that function to the rows. And what function am I going to apply? This all function. Yes, and so we're going to check whether all the rows are true here. And that only happens 90.3% of the time. And so of my days, 90% chance that I'm going to be fine, but there's still about 10% of the days where I'm going to have at least one bad hour. Okay, so that's something to be aware of with your boss is like we set this 95% as our chance constraint. It turns out that for any single constraint, it turns out to be about a 99% chance of passing it, which sounds great. But on a whole day level, it only ends up being about a 90% chance of having a perfect day. So do with that, or kind of that would inform your negotiation with Larry's boss of sort of, okay, are we okay with this 90% of days having at least one bad hour, as long as each individual hour had a 99%? So maybe go back and forth a little bit with the boss there. Okay, so bringing back from our simulation, now we're going to do essentially a combination of the simulation and the chance constraints. So this is stochastic programming with Recourse. So we're now going to say that in the occasional scenarios where there's more tickets arriving than can be processed, Larry has some options. Okay, it's not just the end of the world if that happens, but he has some options. He could potentially he and his managers could step in to answer those tickets, then their work isn't necessarily getting done. You could maybe pay workers extra to say overtime to help clear that backlog. Yeah, he's got a couple of options there. And so Larry estimates that he can do these things, but it costs him on average $10 per ticket to deal with any extra tickets that are over the regular capacity of the full-time and part-time consultants in that hour. Okay, if you think that a full-time worker was being paid $40 per hour and answering on average 10 tickets, then sort of the full-time workers are sort of paid an average of $4 per ticket. This represents a 2.5 times multiple for these extra tickets. So double time and a half, maybe if he's paying his workers overtime, or maybe that just represents the pay jump for his managers. I don't know, but we can actually, and we will, sort of play with this penalty number here of $10 per ticket of overage. So let's modify this problem to allow for this recourse. Okay, so our decision variables, we're going to introduce one extra decision variable, well, actually 16 extra decision variables of this extra tickets, and we're going to have one variable for each of the 16 hours of the workday. Okay. For a stochastic program, there's going to be, stochastic stands for uncertainty. There's going to be some random parameters in the problem. Okay, and so those random parameters are the random parameters that we've sort of been dealing with. They're the service rate, and we're going to have a different randomly generated value of service rate for each hour, as well as the number of tickets arrived. Okay, so tickets arrived, we're going to say that's Poisson distributed. So same distributions for those random parameters as we used in our chance constraints. Now we're just actually going to incorporate those random parameters into the optimization itself. Okay. So our objective is 320 times number of full-time workers, 120 times the number of part-time workers, and 10 times the number of overage or extra tickets. Okay. Our constraints are essentially the same constraints as before. The difference is now we're sort of splitting each shift into 4 hours. So hours 1 to 4, 5 to 8, 9 to 12, and 13 to 16. And we're sort of duplicating the constraints for each of those 4 hours. Now, instead of having a fixed number here, we've got a random parameter for service rate and a random parameter for tickets arrived in that hour. Okay. The ratio constraints are exactly the same as before. Okay. I will say with this recourse problem, we're considering full-time and part-time workers as being hired before we know the randomness. But the recourse of the extra tickets, that is determined after the randomness is resolved. Essentially, we've hired the full-time and part-time workers. They all show up for work. A random number of tickets come in and productivity happens such that there's some extra tickets at the end of the hour. At that point, when Larry knows exactly how many extra tickets he has, is when he essentially pulls out the stops and brings in extra work to cover those extra tickets. And so that extra ticket variable is what we call a recourse variable that you can change its value after you know the randomness realized. Okay. The full-time and part-time workers, you have to choose those before you know the randomness. Okay. And so there's only going to be one version of full-time and part-time workers for each shift, but there's going to be a bunch of versions of the extra ticket variables for each random realization. Okay. I'll maybe explain that just a little bit more as I scroll down here. So that's essentially what I'm talking about here. To optimize with the recourse option, while taking into account our uncertainty, the way we're going to model it is we're going to sample over potential values for SR and TA to get SR with an S standing for which sample it is, and TA with an S standing for which sample it is. And so there's 16 hours. And so originally we sort of had 16 SR variables that were random variables. Now we're going to essentially realize the randomness a certain sample number of times. I'm going to use 200 samples. And so I'm going to get 200 times the 16 that I already had, or 16 hours. I'm going to get, yeah, 16 times 200, so 3,200 realizations of this SR random parameter. Same for the tickets arrived random parameter. I'm going to get 16 hours times 200 different samples of the tickets arrived parameter. Okay. For each sample, we then allow the linear program to optimize and choose the optimal value of extra tickets. Essentially, how many extra tickets do we have left at the end of that hour? And we'll denote that as ET HS, so H for the hour and S for the sample. Okay. How do we incorporate that into our objective and constraints? For the objective, we'll average the extra ticket costs over all the samples. So essentially, we'll take the extra ticket costs, I guess this should be EH with a comma S there. We're going to sum over all the samples and then divide by the number of samples. Okay, so if we're doing 200 samples, we'll sort of add up over across all the 16 hours, all the 200 samples, and then divide by the 200 samples. For the constraints, we get an extra constraint for each sample. And so for the this constraint, where originally in the original problem, it was just one constraint, it is now one constraint for each of the 4 hours for each of the 200 samples. And so we're going to get 800 copies of this one constraint, accounting for the 4 hours and 200 samples. Okay. So yeah, you'll notice that this drastically increases the number of constraints and number of variables in the problem. And so we want to be conservative on the number of samples. It would be nice to just do 10,000 samples, but that would make our problem enormous. Okay, so instead, I kept it reasonable at 200 samples. Actually, the first time I ran it, I did it with 10 samples and then sort of worked my way up to how many samples can I include, and it's still solve in a reasonable amount of time. Okay. So running this through the code is actually very similar to before, but I'll point out some of the changes. So here's the mean tickets per hour replicated 4 times for each of the 4 hours in each shift. Otherwise, the rest is the same. I've actually named now some parameters for the cost of full-time workers, part-time workers, and extra tickets. When I add my variables for full-time workers and part-time workers, those stay the same. But now I'm going to add a variable for those extra tickets. It's going to have 2 indexes, H and S. H goes 1 through the number of hours, which is 16. And S goes 1 through the number of samples, which in this case, I've set the number of samples to 200. Okay. I went ahead and set this to a continuous variable. Really, I should probably do this as a integer variable, but that's fine. Okay, so that's our variables. And so in this case, we've got 7 variables for full-time and part-time together. We have 3,200 variables for the extra tickets if we consider the 16 hours and the times the 200 samples. So lots of variables added to the problem. For the objective, this is essentially the same as what it was before. Full-time cost times the sum over all the full-time workers plus part-time cost plus the sum over all the part-time workers. Now we're going to take the extra ticket cost, divide it by the number of samples, and then sum over all the extra tickets for all the hours for all the samples. And we want to minimize that. For our constraints, we're going to generate a random number, just one random number. And it sort of worked out that even if I put 1 there, it would generate 1 for each and they'd actually be different. I did make sure to kind of check that it's generating different random numbers, not duplicating the same random number over and over again. But it will be at our mean service rate and with our standard deviation for service. We'll multiply that by the number of workers on the shift. And then add on whatever extra tickets that we need to deal with. And that has to be greater than or equal to our Poisson, which is going to be a randomly generated Poisson value, we're going to generate one value with a parameter equal to the mean tickets for that hour. So mean tickets change throughout the shifts and throughout the hours through the day. And we're going to repeat this constraint for H equals 1 through 4. So the first 4 hours, which is that first shift, and S for 1 through number of samples. So there are going to be 4 times 200 samples versions of this first constraint. So now we sort of have 800 copies of what was originally just one constraint. We repeat that for each of the other shifts. I'll maybe point out that the ratio constraints, nothing happens with them. They stay the same. They only involve the non-recourse variables, the variables that we don't change after randomness. If we solve this out, we'll get an objective value of about 4,700. Here's our scheduling plan, which is 334 for full-time workers and 1332 for part-time workers. You'll notice that this is almost identical to our original solution when we were just meeting the average demand. In that case, the only difference was we only had 2 workers for shift 2 for part-time workers. We've now upped that to 3 workers. Okay. And if you do a little bit of thinking, that shift 2 was the shift with the highest average number of tickets. And the way the Poisson distribution works, it also would have the most variability in number of tickets. And so that's the one place where we decided we needed an extra worker to handle what could be spikes in the number of tickets arriving during that hour. Okay. This works out to about 14% more than the original solution. But of that 14% more, 3% is from the extra staffing costs of that one extra part-time worker. The remaining 11% is the extra cost of the recourse actions. And if you'll note, our first solution didn't include the recourse actions. And so really, we might actually expect that if we were to kind of solve the original solution with the recourse actions, we'd do worse than this. Okay. This is an estimate based off of only 200 samples of what the cost would be for this staffing plan. Okay, the extra ticket variables are sort of random realizations of what might happen. Okay, if you wanted to get a better estimate of what this plan here would actually cost you, you'd probably you'd kind of fix your optimization. So you've chosen this is your staffing for your shifts, and then you'd run 10,000 repetitions of a simulation similar to what we did in our simulation up above. Okay, where you're just simulating and you're not optimizing. Okay. I'm not going to do that right now, but you could. It'd probably give you a number somewhat close to that, but maybe a little bit more, maybe a little bit less. Actually, probably a little bit more because it's not optimizing. We're sort of, in some sense, we've tuned this to exactly the 200 samples that we optimized over. So we might expect that we might do a little bit worse than that when we kind of do 10,000 samples where we're not optimizing. Last thing I want to kind of wrap up with is it's interesting to look at that cost associated with those extra tickets. If we set it to 0, then we're essentially ignoring the cost of extra tickets. And then we're essentially back at what should be our original solution. Okay. Where we're just have enough workers to meet the average demand. Okay. On the other hand, as we raise it, we should get closer and closer to the robust optimization solution, which would be the worst case. And you can kind of think of the worst case as what we want to have if the cost for extra tickets was enormous. Okay, if there was a catastrophic cost from having even a single extra ticket, we'd choose the robust solution. Okay. Essentially, that cost of extra tickets, as we increase that, we're changing our constraints from soft constraints where there's a moderate cost to violating that constraint into hard constraints where there's a much higher cost for violating that constraint. Okay. Essentially the big M method where we sometimes let M not be enormously huge. Okay. And this is the value of kind of learning the big M method, is that you can actually use it to change some of your constraints into soft constraints. And you could use a moderate value of M if you're willing to let some of those constraints be violated, but maybe at a slight cost. Okay. In the extreme, if we set the extra ticket cost to 100,000, which is much more than the staffing cost, it will force all the original constraints to be satisfied. Okay. And that for all of the samples. So there's no sample where we violate any of the constraints. And we get 0 extra tickets for all of the random sampled versions of the constraint. And if you solve that out, you'll get this solution down here, which is actually not even as bad as the robust optimization's worst case scenario. You pay 50% more, maybe about 53% more than the original solution, which isn't as bad as the 60% more than the original solution. This last line here is just checking that the only variables in that solution that are bigger than 0 are the staffing variables of full and part-time workers. None of those extra ticket variables ended up being non-zero. So that wraps it up for this example. I encourage you download the code, kind of look through some of the bits in the code. There are actually very little changes going from one to the next to the next. And so I encourage you, as you're doing other problems, think about, okay, what would I do if some of these parameters were uncertain? What would I change in how I formulated my linear program to maybe account for some of that uncertainty? That's it for this video.